Hello everyone, I am Lalit Sharma from the Venkateshwar School, Gurugram. Today we will discuss about torque experienced on a current carrying loop when it is placed between external magnetic field. So let's start. Students, this is a loop PQRS whose sides are A and B, and current flowing in this loop is I, and it is placed between two poles of a magnet, north and south, and we know direction of magnetic field is from north to south, and if angle between normal of this plane and magnetic field. So if we consider these things, then it will experience torque, and how and what is the amount of torque we will calculate now. Students, we know if a current carrying conductor is placed in magnetic field, it experiences some force, and whose direction is given by Fleming's left hand rule. So if we apply Fleming left hand rule on this arm, say PQ, current is flowing from P to Q and magnetic field is from north to south. If we apply this rule, if we stretch our first finger, central finger and thumb mutually perpendicular to each other, first finger points to the direction of magnetic field, central finger to the direction of current, and thumb will denote the direction of force. So if I apply this rule on this arm, current is flowing from P to Q and magnetic field is from north to south, my thumb is pointing inwards, so force experienced on this arm PQ is inwards. And similarly, if I apply on this arm RS, this is the direction of current R2S, and this is the direction of magnetic field, so thumb is pointing outwards, so RS will experience force in upward direction and PQ will experience force in downward direction. So there is a couple formed, and due to which this loop will try to rotate, and now we will calculate what is the rotational effect of force, means what type of torque or how much torque is experienced by this loop. So if I take this section only, QR, here this length is A, and here what is happening on this end, force is upward, and at this end force is downward because it is rotating like this. So if this angle is theta, then this perpendicular distance between the force on opposite ends, this perpendicular distance is A sin theta, and we know torque is force into perpendicular distance, and we know force experienced on a current carrying conductor is BIL. L is the length of the conductor, I is the current flowing, and B is the magnetic field. So BI and B, this is the length B, and perpendicular distance is A sin theta. So torque experienced on arm PQ or RS will be this. And students, we know if length into breadth, A into B, this is the area of this rectangular loop. So B and A, it is written like this. This product of B and A is A, area of loop. So now our torque is BIA sin theta, and if there are number of n turns of this loop, then torque is NIBA sin theta. And one more thing you have to keep in your mind, that if a current carrying loop is there and I is the current flowing and A is the area of loop, and then current into area is the magnetic moment of the loop, because that loop acts as a magnetic dipole whose one end acts as north pole, other face acts as south pole. So magnetic moment of that loop is given by current into area, and if n turns are there, then NIA is termed as magnetic moment small m. So this relation becomes MB sin theta, and as M and B are vector quantities, if I term this formula in vector form, then torque is M cross B. It is a cross product of magnetic field and dipole moment, magnetic dipole moment. So this is the torque experienced when a current carrying loop is placed in magnetic field. Students, on this concept, in the basis of this concept, we will discuss moving coil galvanometer